For today we're starting section 4.1 and we're going to talk about divisibility of numbers. So it's going to involve some of the division things that we did in the last section, but from a little bit different perspective. So the first thing that we're going to take a look at is what the definition is of divides, what we mean by divides. So if we have two whole numbers, A and B, then we would say that B divides A, and it is written B with a vertical bar. This notation is really important because it does not mean it's a fraction. This is not B with a horizontal bar and an A below. That's exactly the opposite of what it says, in fact. It says that the first number divides the second one. So for instance, we could write something like this: 2 divides 4. And it does, right? 2 does divide 4. So that's how we would write that, and that's what that would mean. And this is true if and only if there is a whole number q such that A is equal to B times q. So the reason that 2 divides 4 is because there exists a number 2, that's the q that it's referring to, such that 2 times 2 equals 4. That's what this definition is referring to. So here's another example without the 2 in there. 4 divides 20. We can also say 4 is a factor of 20. Or 4 is a divisor of 20. All of those statements are exactly the same meaning. Sound different, but they mean the same thing. And then the last one, 20 is a multiple of 4. And the reason all of these work is because if we think about this notation, what this is saying is there is a number that I can multiply by 4 and get back to 20, a whole number. We're only working with whole numbers still, whole numbers, okay? And what number should go in that box? 5. It would be the number 5.
So does the smaller number go on the left side?
If there is one that is smaller, yes. But it could be that you have, for instance, the same number, right? Because 4 divides itself too. But if one of the numbers is smaller than the other one, then the smaller one would come first. But just because you have two numbers and one of them smaller doesn't mean it has this relationship, right? In other words, I can't write this. That doesn't work. 3 does not divide 4. But we do have a notation for that. I can't remember if I get to it now or later. I'll mention it now just in case I don't have it in there later actually written down. If we would say that 3 does not divide 4, just like when we've done things before, we would put that slash through it, just like a not equal slash. Or we did not an element of slash. You just put the slash through that symbol. It's the same thing. So 3 does not divide 4.
So does q equal like 5 in that sense right there?
Yes, this would be the q value right here. Yeah. And again, it's important to realize that q has to be a whole number, right? I can't have q be a fraction or a decimal or something like that because we're not working in the fractions and decimal number system. We're not working there yet. We're only working with whole numbers. So we're still talking whole numbers here. All right, our first theorem, and we're going to have quite a few, is that if we have whole numbers a and d, and if d divides a, and n is any whole number, then d divides n times a. So let me just give you an example here so you can see what this means. Let's use that 4 and 20 above. We know 4 divides 20, right? Well, that also means that 4 divides 20 times 3. Well, 4 divides 20, then 4 divides 60. And I can put any whole number here and it'll work. 3 is not special. 2 would work, 7 would work, 14 would work. Anything would be fine. So as long as 4 divides one piece of it, it divides all of it. And that's how you guys make decisions about numbers being divisible by 2, isn't it? You really just look at it and you say, well, does 2 go into a part of this? Really, you're looking for, is it even? You're doing the same sort of a reasoning when you work with the number 2. All right, next theorem. And there are multiple parts to this one. 5 parts to be precise, right? Okay, let's get the first one written down. So, if D divides A and D divides B, then D divides A plus B. So if you could separate it into two pieces that are both individually divisible by the number, then the sum is divisible by the number. We'll do some examples, I promise. If D divides A and D does not divide B, then D does not divide A plus B. So it feels a lot like the first one, right? Once we negated basically one piece of it, it negated the result. Okay. All right, the third one, if D divides A and D divides B, we're going to put the condition A is greater than or equal to B, and I'll tell you why in a minute. Then D divides A minus B. So the hypothesis, the first part of this, the premise, is the same as part A, right? Identical, the same, except for this one additional consideration. Why do you think I need A to be greater than or equal to B? So I don't get negative numbers, because I'm supposed to still be working in whole numbers here. Now, it's true if it were a negative number. We're just not working in the negative numbers. Does that make sense? So this condition is just really just to keep us in the whole number system. That's it. And so if I subtract the numbers, I will still get something divisible. So this is the same thing that happens, right, when you guys do things like an even plus an even is an even. An even minus an even is still an even. And you're still able to say that the result is divisible by 2, whether you add or subtract. All right, the third one, or fourth one, excuse me, part D, looks a lot like the conditions on part B. If D divides A and D does not divide B, we're still working with the A greater than or equal to B just so that we stay in the whole numbers. Then D does not divide A minus B. It's essentially the same analog we had before, right? If you make one piece of it different, the result is exactly the opposite too. Right? Even minus odd is odd, so it's not divisible by 2. That's kind of what's going on. Last one. If D does not divide A and D divides B, still again A greater than or equal to B, then D does not divide A minus B. And all this is doing from part D is simply saying it really doesn't matter which piece of it fails to divide, it's still not going to divide the final result. Okay, so it could have been done in other words in any order, in either order. The reason we don't have a sort of part in here after AB like this is because when we're adding A plus B is equivalent to B plus A. So we can just switch those and it doesn't actually change the problem at all. But it does down here, right? Here you would actually have an even minus an odd versus an odd minus an even or something like that. And it actually changes the result of the solution because we don't have commutativity of subtraction. So that's why there's a fifth part on that piece that there wasn't on the other one. Okay. You guys ready to do some that are actual ones that you can work with numbers on now? Yes, Kenzie.
What if it's like if B is not, if they're like both not, because couldn't it still be?
It could, yes. So if you have, because we don't have a theorem about it, right?
Yeah.
But if you did have this that it doesn't divide either piece, could it divide the result? Yes. Does it have to divide the result? No. It would just depend on what values you were looking at. So if we were talking about like the even and odd case, right? And you did it with addition, let's say, then when you actually add an odd plus an odd, neither of which are divisible by 2, you actually do get something that is even, which is divisible by 2. But if we were working with something besides odd or even, where it's just one or the other, that wouldn't have to happen. For instance, something that's divisible by 3 added to something that's divisible by 3 is divisible by 3. But if you make them both not divisible by 3, you might get something divisible by 3 and you might not. So it's not a for sure either way if we don't have these conditions. Does that help? Okay. All right, we're going to do some divisibility tests for some specific numbers. Now, you guys know some of these. In fact, I've already used the first one in lots of what I've verbalized on the last slide, right? So when is a number divisible by 2? If it's even. What do we mean when we say it's even? How do you identify if something is quote unquote even?
Ends in an even number.
Okay, if it ends in an even number, that's important, right? All the numbers at the beginning don't really matter. It's the ending number that matters. And what do we mean by even for the ending number to be even? 0, 2, 4, 6, and 8, right. So a whole number is divisible by 2 if and only if it ends in a 0, 2, 4, 6, or 8. Because see, what you want to remember is that idea of even has been so ingrained in you that you just look at it and you know. But if you were explaining this to somebody for the first time, what would you say they needed to look for? Well, they need to look at the very end of the number, like you guys said, and they need to look for specific numbers to be that end number, 0, 2, 4, 6, or 8. How about 5? How do we decide if a number is divisible by 5?
The end is in 0.
Good. So it ends in 0 or 5. And then how do we decide if a number is divisible by 10? Yeah. It ends in a 0. So all of these are kind of grouped together because the rule's the same. I mean, the numbers are different that we're looking for, but what we're doing to identify them is the same. We're looking at the end number. Not all numbers have this ability. If I'm looking for something to be divisible by 3, I can't simply look at the last digit. It doesn't work that way. But for 2, 5, and 10, all I have to do is look at the last digit and make these sort of adjustment decisions, right? I look at these and identify which one works. Okay, so the next two are grouped together again because they're similar. Does anybody know the divisibility test for 4? This is not all that common, so you may not, but does anybody know it? That's okay, that's right. So with the number 2, we look at the last digit and we say, is the last digit divisible by 2? That is 0, 2, 4, 6, or 8. Well, with the 4, we actually look to see if the last 2 digits as a number, I'll show you what I mean by that, are divisible by 4. So let's say we had this number, 42,043. We take the last 2 digits and we focus on them as a number in and of themselves. This is the number 43. Okay, we say 43, and we ask ourselves that same question. Is 43 divisible by 4? The answer is no, and if the answer is no, then the whole number originally that was longer is also not divisible by 4. Okay, so we just isolate the last 2 digits, and we look at them as one whole number combined. Yes, Hannah?
Is there one divisibility test where you add up all of the numbers? Okay.
Yeah. Yeah, we're almost there. We're really close. It isn't the next one, though. But yeah, we'll get there. There's actually 2 of them that have that property. Divisibility test for 8, you look at the last 3 numbers. That's right. So if you do the divisibility test for 2, you look at the last digit. If you look at the divisibility test for 4, you look at the last 2 digits. And if you do a divisibility test for 8, you look at the last 3 digits. Now, this isn't the most helpful of all divisibility rules, because I suspect that when you look at the last 3 digits of most numbers, you're not going to know any more than you looked at the original number. But you could do the math for it much more quickly if that's all you were trying to find out, right? If you had a 17-digit number and you wanted to know if it's divisible by 8, it'd be much easier to divide the last 3 numbers to decide that. So it's at least easier to work with to some degree. So on this one, we look at the last 3 digits as a number to see if they are divisible by 8. And again, I'll write down an example just for fun here. So I have 67,438. I would look at these 3 digits as a 438 number, and we would do a real quick division in whatever way you would like, and you would see, is that divisible by 8? If the answer is yes, then the whole thing was divisible by 8. If If the answer is no, then the whole thing isn't divisible by 8.
Okay.
I think my next slide gets to where you want to be, Hannah. Yes, it does. All right, a whole number is divisible by 3 if and only if. Okay, these two, again, they're grouped together because the process by which we make the determination is similar. So this is the one that Hannah's mentioning. We add up all of the individual digits in our number together, and if the sum is divisible by 3, then the original number is divisible by 3. Okay, so a whole number is divisible by 3 if and only if the sum, use black, the sum of the digits is divisible by 3. So if we had the number 413,629, we would add up 4 plus 1 plus 3 plus 6 plus 2 plus 9. That's what we would do. So we'd say 4 plus 1 plus 3 plus 6 plus 2 plus 9. We'd get some value, whatever that value is. If that value, which is much smaller than the 413,000 number, if that value is divisible by 3, then the original number was also divisible by 3. It's a handy-dandy trick. The cool thing is, though, it works for 9s as well. It's exactly the same rule. I mean, no different at all. It's just at the very end, kind of like the 2, 5, and 10 rule. At the very end, you just look to see if the final result's divisible by 9 instead of divisible by 3. So a sum is divisible, or a number is divisible by 9 if and only if the sum of the digits is divisible by 9. So we would go through the exact same process. We just add all these digits together. We just look at the final result. Is the result divisible by 3? Then the number is divisible by 3. Is the result divisible by 9? If it's yes, then the sum is divisible by, the original number is divisible by 9. All good? Okay, I think that's all the rules for the moment. Am I right?
No.
Is there one more page? Oh, yes. 11s and 6. I forgot about those. All right. The 11 one is so much harder to write out than it is to see. I'm going to write it out because your book does, but then when we do one, I'll show you how much easier it is to actually see. So a whole number is divisible by 11 if and only if the sum of the digits in the even powers of 10 minus the sum of the digits in the odd powers of 10 is divisible by 11. Who wants to do an example? You know exactly what that means now, right? Perfectly clear. Just like saying, look at the last digit. Is it a 2? Oh, it's even. Not so clear. It doesn't look so clear. Here's what you really do. Here's what this is telling you. I'm going to give you a long number just so that we can talk about it in this way. 4, 7, 6, 2, 3, 9, 4, 1, 7, something. I don't know. We've got a long digit. What you do is you identify every other digit. Okay, so I'm going to just circle every other digit. Okay. Some of those digits are the even powers of 10. The other digits are the odd powers of 10. Right? Like this one right here is 10 to the 0. This is an even digit of 10. It's an even power of 10. This right here is 10 to the 0, 1, 2, 3. It's 10 to the 3, so this is an odd power of 10. So that's what this even odd business is talking about. What it's saying is you go every other number. So we've circled every other number. All the numbers in red, we add them together. All the numbers I didn't circle in red, we add those together. Okay, so let's do this real quick. I have no idea what this answer is going to end up working out to be. It's probably going to be no. Most numbers are not divisible by 11, so if I really looked upon one, that would be very interesting. So what happens when we get 4 plus 6 plus 3 plus 4 plus 7? 24? Okay. What happens when I add the ones that are not circled? 7 plus 2 plus 9 plus 1? 19. So you take the 24 and the 19 and you subtract them. How far apart are they? 5. Is 5 divisible by 11? No. Then this original number wasn't either. So the process itself isn't hard, but there's no real clean, concise way of writing out what I just did. Do you guys see what I mean? So we just circle every other number. We add up the ones we circled and we add up the ones that we didn't. And we subtract those two sums. 24 and 19. Yeah, it doesn't make any difference. Yeah. It's kind of like looking at the numbers, whether you're looking at, yeah. And we could say the sum, and it says here minus, we could say the difference between, then we don't have to worry about which ones we subtract from which. Because just like I mentioned back at the, I don't even know which slide it was, maybe the third slide, this one right here, this whole conditioning right here doesn't really change the answer. It just changes whether I'm actually looking at positive or negative numbers. And we haven't really talked about negative numbers yet. That's in chapter 5. So we're just trying to avoid the negative number bit for now. Okay, but it actually works for negative numbers as well. So yeah, so we just subtract 24 minus 19. Here I'd get 5. Since 5 is not divisible by 11, the original number wasn't either. Okay, divisibility test for 6 says the following. A whole number is divisible by 6 if and only if it is divisible by 2 and 3. Why should that work? Yeah, it should work. It seems reasonable anyway, because 2 times 3 is equal to 6. Now there's one condition that you don't notice happening here that makes this work, because this doesn't work for all numbers. For instance, if I wanted to find out if a number is divisible by 12, I can't simply look at 2 and 6 and say, is it divisible by 2? Is it divisible by 6? Since it's divisible by 2 and 6 is divisible by 12. I can't do that. What's the difference when I consider 2 and 6 as to when I consider 2 and 3? Okay, part of it has to do with being prime, although we don't have to have something prime.
All the lower numbers can only multiply that number times 1. That's like the first number where you get.
Okay, that's the prime issue. That's the same issue that Morgan mentioned, yeah. So, or Katrina, I don't remember, one of you guys said it. Morgan did it, okay. So, yeah, we sort of have this feeling of, well, maybe it's because it's prime. And certainly if 2 numbers are prime numbers and they multiply, this will work. So if I wanted to know if a number works to be divisible by 15, I could test to see if it's divisible by 3 and 5. And that would work, because 3 and 5 are both prime. Okay? Let's use the number 12 one more time, however. If I wanted to know if a number is divisible by 12, I cannot use 2 and 12. 2 and 6, excuse me. I can use 3 and 4. What's the difference between 2 and 12, 2 and 6, excuse me, I said it again, 2 and 6, and 3 and 4? Because 3 and 4 are not both prime now, are they? Okay, but if I factored 6 down, it was 2 and 3.
Because 2 squares work, so it's like a square number.
Nope, that's not going to work all the time.
Is it because if you put all the factors in a list, you should do 1 and 12 and 2 and 6, it would be mostly.
Good guess. It's not because it's the one in the middle, though. That's a good guess. Here's the difference. When you look at the numbers 2 and 12, I'm sorry, 6, 2 and 6 making 12, compared to 3 and 4 making 12, those two numbers have a factor in common. 2 and 6 are both divisible by what? 2. 3 and 4? They don't have that, do they? There's a special relationship that exists when the two numbers, they don't have to be prime, but when the two numbers have nothing in common with each other. That is, they don't have any factors in common except for 1. They've always got the number 1 in common. In this case, when we're talking about the 3 and the 4, 3 and 4 are what are called relatively prime. We'll get to it either the rest of this end of this lesson or the beginning of the next one. But the phrase simply means that they don't have any prime factors in common. All right? So 3 and 4 are not both primes, right? Because 4 can be broken down, like you guys have already told me. But when you break it down, it doesn't become anything that has factors of 3. That's what it takes. So this rule down here, this divisibility test for 6, is a much broader rule. It doesn't really just apply to 6. It applies to anything where you can break it down into factors that don't have anything in common. So 15 would look just like 6, right? Because I can do 3 times 5. 12 would look just like 6 because I can do 3 times 4, but you can't do 2 times 6. Okay? So we'll come back to this one and this idea a little bit later too. Okay. Here's a number for us. 24,015. We're going to decide if the number is divisible by each of the following without using a calculator. So what that means you need to be doing is using these rules. So if I ask this question on a test, even if your book doesn't phrase it this way, you're going to have to justify why it works. And I put it in my calculators, not going to work for good justification. Okay? So starting with 2, is it divisible by 2? No. Why not? Right. It doesn't end. It doesn't end in a 0, 2, 4, 6, or 8. And we're just going in order. 3. Is it divisible by 3? How do you know? Yes or no? How do we decide? Okay, Hannah says yes. Why? Okay, so when you add 2 plus 4 plus technically 0 plus 1 plus 5, what did you get? 12. Is 12 divisible by 3? Yes. So the original number was as well. Okay, so I'm going to use some notation that you're not comfortable yet, and that's okay. What does this say? Okay. 3 divides 12. Okay, it means 3 is a factor of 12. It divides into the number 12. Okay. How about the number 4? No. Why not?
15 isn't.
Right, 15 is not divisible by 4. That's all you have to check, right? In fact, the very fact that it's not even already means it can't be divisible by 4, right? It wasn't divisible by 2, so there's no chance it's going to be divisible by anything even. How about 5? Oh, I'm sorry.
Could you say for that one, 4 divides with the line through it and 15? Yeah.
Like that?
Can you do that?
Yes, you can. 4 does not divide 15. Perfect. And we could say up here then that 2 divides, 2 does not divide the 5 at the end. Yeah. That's what we're actually making the claim about. How about 5?
Yes.
Yes, why?
And it lasts.
It ends in a 5. So again, we could say 5 divides 5 because the 5 at the end is the one we're checking, and we're trying to see if it's divisible by the number 5. What do we have next? 6.
No.
No, why not?
Because it's divisible by 3, but not 2.
Right, because it's not divisible by 2. It's not divisible by 2 and by 3. It can't be divisible by 6. So 6 does not divide 24,015. Now I'm not looking at specific digits. I'm looking at the whole sum. I didn't have a specific digit I was looking at on that one. Let's see, 8. No, why not?
Because you're basically looking at 15 again.
Right, because we actually have a 3-digit number that starts out with a 0, right? 015. It is not divisible by 8. So again, 8 does not divide 015, or 15 specifically. How about 9? Carrie, you said no. How come?
Because 12 is not divisible by 3.
Yeah, this same value right here that we did for 3 gave us a 12 down here, and it is not divisible by 9. Divisible by 3, but not by 9. So 9 does not divide that 12. 2 more. 10. No, why not? It does not end in 0. Right? So basically the issue is that 10 does not divide that 5 at the end.
We were having to explain grouping, but because it's not divisible by 10.
You could. 10 actually works with that same divisibility rule that 6 does, because 10 can be broken down into 2 and 5, which means it both has to be divisible by 2, and it has to be divisible by 5 to be divisible by 10. You could. Last one, 11. It's the weird one. Let's actually do it because, again, it's not difficult. It's just a really weird description of how to do this problem. We circle every other digit. Okay, the ones that I circled sum up to what? 7. And the ones that are not circled add up to 5. And what's 5 minus 7? 2. Does 2 divide is 2 divisible by 11? No, so this one doesn't work. So 11 does not divide 2.
If that's on the test, can I just show that and say 11's not divisible by 2 instead of like writing out?
Well, I wouldn't ask you on a test to write out one of these rules specifically anyway. I might ask you to describe how you know something, and what I've written here is a shortened form of what a description would look like.
Okay.
So you would use some words to encompass this. I added all these digits together, and when I found out their sum was 9, and 9's divisible by 9, so yeah.
Expect us to be able to say
You don't have to say it with the even and the odd digit values, no. No, this is fine. So 11 does not divide 2 here at the end, so the original number is also not divisible by 11. All right, a little bit of a variation of this. We're going to take a look at some true-false questions, okay? So the following we're going to classify as true or false. It says, if a number is divisible by 6, then it is divisible by 2 and by 3. Is that true or false?
False.
False. Why?
Because if it's divisible by 6, then it can end in a 3. So it's not even, so it can't be divisible.
Can it end in a 3 if it's divisible by 6?
Yeah, because if it's divisible by 6, then it's all automatically divisible by 2 and 3.
It actually works to have, and if you want to think about, Hannah with me, if you want to think about your multiplication tables of 6s. We can go up, we don't have to go up forever, but if we just go up the basic ones of them, we start with 6. What's next? 12, 18, 24, 30, 36. I know you all stopped on me. They're all even, right? Yeah, so this is actually true. If it is divisible by 6, it has to be divisible by both 2 and 3. It's actually true. Now, part B is a little different. Part B says if a number is divisible by 2 and by 3, then it is divisible by 6. That's also true. And if you take a look back at that divisibility rule by 6, I'm going to flip back here so you can see it and I can see it at the same time. This divisibility test for 6, there is a phrase in here that's really important that tells us we can read that in either direction. Do you know what that phrase is? It's the if and only if phrase. That phrase, if and only if, means you can read the direction or you can read the description in either direction. So you can say a whole number is divisible by 6 if it is divisible by 2 and 3. Or you can say if it is divisible by 2 and 3, then it is divisible by 6. The if and the then can go either directions when you have an if and only if statement. Yes?
Okay, so basically like the same number has to be divisible by 2 and by 3.
Right.
Okay.
And if that same number is divisible by 2 and by 3, then that number is divisible by 6.
Okay.
And likewise, if you were to take your calculator, for instance, and just divide something and find out, hey, it's divisible by 6, you would know automatically it's divisible by 2 and it's divisible by 3. So those go in either direction. Now it's a little different for the next two, so pause with me and think. This one says if a number is divisible by 2 and by 4, then it is divisible by 8.
False.
That is false. Now, when we do something that's false, it's a good idea to write down an example of a case where we know it doesn't work, so we can actually say, hey, look, I found one. Can you find one? Oh, can we do an easier one, Marilyn?
Okay.
Something easier.
44.
44. That will work. I like 44. Okay. 44. Is 44 divisible by 2? Yes. Is 44 divisible by 4? Yes. Is 44 divisible by 8? No. So something small and simple. If you want to do something creative, that's fine. But something simple is fine too. Okay, so this one, it didn't work. Right? How about the other direction though? If a number is divisible by 8, well, this says if and only if. So a number is divisible by 8 if and only if it is divisible by 2 and 4. So this is tricky. Remember what did I say about if and only if? Has to go both ways. So this has to be false. Why?
Because if 2 and 4 are. I can't get my words right. If the number isn't divisible by 8, if it's divisible by 2 and 4, then
Right.
why would it be the opposite?
Well, it could be the opposite, but this if and only if part right here means it has to go both directions. One of those directions was what C said, right? And we already said C didn't work, at least not for all numbers. Like there are examples of numbers for which it doesn't work, so it's not an always true statement. So the if and only if messes this up. Now, what if it didn't have the if and only if? So let's pause for a moment. Let's call this example E. And let's say we had the same thing, but instead of having the if and only if, it just said the following. If a number is divisible by 8, then it is divisible by 2 and 4. Then that is true. If it's divisible by 8, it is definitely divisible by 2 and 4. And you know what? You actually already had something that said that worked, but you probably didn't recognize it at the time. So you can flip back if you'd like. I'm going to, and I'll show you which one it was. Whoops, one far. It's Theorem 4.1. Theorem 4.1 says that if you have a number that is divisible and you multiply it to get something larger, it still works. This example with my 4s and my 8s is a variation of that. Right? If it's divisible by 8, it has to be even, right? Well, yeah. I mean, all of your multiples of 8 are even. So you get the 2 one sort of for free. And the same issue with 4s. I mean, like if you think about your multiplication tables for 4s. Let's try this together. 6s didn't go so well. 4, 8, 12, 16, 20, 24, 28, 32, 36. Let's stop. Okay, so we've got 36. Now, thinking about those numbers, let's do the multiplication tables for 8s. We won't go up as far. 8, 16, is it divisible by 4?
Yes.
What's after 16? 24, is it divisible by 4? Yeah? 32, is it divisible by 4? Yeah, it's actually the same list. It's just every other number, isn't it, in the list? It's not by coincidence. That's really how it works on purpose. So that kind of an issue right there is what this is getting at on the last one. If we change the if and only if to only go one direction. So if this had been the question, then as Katie said, this would be true, actually. Okay. Okay. Let's try another one. Example 3. We're going to answer each of the following again without performing the division. Now, what's weird about this one? Look at A, B, and C. What do you see here?
17 numbers.
Weird numbers, right? I mean, these were not in my list of numbers that we just went through divisibility rules on, right? So we're going to be having to do something a little bit different on these, obviously. The 5s down here are a little bit different. In fact, these numbers are also a little bit different on D and E. What do you see about D and E? I got some things all multiplied out, not the actual number itself, right? Okay, so let's start with the first 3. 17. How can we decide if 17 divides into 34,015?
Should we do the 7?
We don't have a divisibility rule for 7, but even if we did, it wouldn't help on this one.
Could you find the divisibility of 17? And then,
Like make up a rule about 17?
no,
Not make up, but discover.
like find if 17 is divisible.
17 is already prime, so it won't actually be helpful. But yes, if we had a number, for instance, say like 18, and we wanted to break 18 down into pieces, that would be a good way to start. The 17 doesn't work with this one, unfortunately, nor does 19. You guys saw something in the last chapter that would help you here.
You could break it apart.
You could break what apart,
Like
Marilee?
if you did the 30 per thousand, if you did 34 divided by 17, that's 2. And you can't divide 15 by 17, so you know that's not, like it won't work.
Yeah. Remember we had this sort of a, it looked like this. We took the 34,000 and we wrote it as 34,000 plus the 15. Something weird like that was the notation. It looked a little awkward. But we said, hey, if I just notice the 34, it's not big enough that you shouldn't be able to do it pretty quickly. It goes into, 17 goes into that twice, right, with no remainders. So it evenly divides inside of or into the number 34. But it doesn't do that with the number 15, right? Right? So 34, let me write this way, 17 divides the 34. But at the end, or the 34,000 if you want to write it that way, but the 17 does not divide the 15. It doesn't work at the end when we're sort of breaking it into pieces. So on this one, the answer is no, it's not divisible. And again, if you were justifying, you would put more words with what I just wrote, right? You would use some language revolving around this. You know, oh, I noticed that if I break this into pieces, like Marilee said, the 34 will evenly divide into 17, but the 15 doesn't, that kind of thing. What about 34,051? You could do the same thing. Do you think the result's going to be different? Yes. I probably wouldn't ask it if it weren't, right? So we already know that the 17, I have that written wrong. Nobody corrected me. Up here, it was supposed to say divides. I already know that the 17 divides the 34. Does the 17 divide the 51? Morgan says yes. What would it be if I tried to do the division? It is. It's evenly in, goes in evenly 3 times. So 17 times 3 is 51. So this is divisible in both these cases. So does this divide evenly by 17? Yes, it does. And you guys have calculators. You can confirm your answer very easily, right? So there's absolutely no excuse for not being able to get the answer right to any of these. There's no excuse. Now, whether you can justify your answer with reasoning that's with what we're looking at, that's a little different. But being able to say yes or no correctly shouldn't be the problem. Does that make sense? So let's try another one. How about 19,031? Couldn't you do the same thing? Sure, why not? What if we break this one apart? 19,000 and then 31. Does it work? It goes into the 19,000, but it does not go into 31. It's a 38. That would work. 31 doesn't. All right, this one's interesting. This one says 2 times 3 times 5 times 7. And you absolutely have no reason to multiply that out to find the answer. Does this number divide by 5? Yes. And there's a lot of reasons why. You could show me why. So somebody give me one. How do you know? Okay. 7 times 5 is 35. Okay, so say that louder for me, Kinsey.
Because the numbers being multiplied by 5, so it's divisible.
Yeah, so all of this right here, all multiplied out or written in factored out form, includes a digit as one of its factors. That's 5, right? So if I were to multiply this out, how would this number have to end? A 5 or a 0, because it's got a multiple of 5 inside of it, a factor of 5 inside of it. This has to end in a 5 or 0. There is a factor of 5 inside of it, which means it is divisible by 5. And again, we could go back to theorem 4.1, the very first theorem. It said the same thing. Okay? Since 5 is divisible by 5, 5 times anything is divisible by 5. So this would work.
If we were to write that on a test because there's a factor of
Uh-huh.
5 in there, that would be okay?
Yeah, that's exactly why. The factor of 5 tells me. But the last one right here, which we'll stop with, of course, today, is different. What's different about the last example? What does this plus 1 do? It changes the resulting answer. That is, if I simplified everything that's all written at the beginning. How will this number end? In a 1 or a 6? Why?
Since there's a factor of 5, it's either going to end in a 0 or a 5, and then you tack on the 1.
Very good. Did everybody hear Hannah? Okay, I'll say it a little louder, and that way it'll pick it up on the iPad too. This number without the plus 1, you knew it ended in a 5 or a 0. We did that on the last problem on part D. Adding the 1 to it then means that it ends now in either 0 plus 1, which is 1, or 5 plus 1, which is 6, neither of which are then divisible by the number 5. So this one's no.
So would you like write 5 is not a...
You could write 5 does not divide.
Or yes.
2 times 3 times 5 times 7 plus 1, like that. And then we could write the other one above, 5 does divide. All right, so we will stop there today.